Hello students, this is the last part of the lecture series on microelectronics. It is focused on the applications of logic gates. There are operating conditions for a power supply of 5 volts. As shown in the table, logic gates are used as switches. When the input conditions are right, they switch on an electrical device. The working conditions for logic gates depend on the type. For the input, the logic state is 0 if the potential or voltage is less than 0.4 volts. It is at logic 1 if the potential is more than 3.5 volts. For the output terminals, the logic gate is 0 if the potential is nearly equal to 0 volt. And it is at logic 1 if the potential is nearly equal to 5 volts. So we say an input potential of between 0.4 volts and 3.5 volts could cause what they call as faulty switching. As our first example, we have here a circuit diagram for an automatic light switch. Right? So in bright daylight, the resistance of the light-dependent resistor or LDR is about 100 ohms. Okay, this is the symbol for LDR. So at that resistance, which is relatively low, what happens is point A is nearly at 5 volts, since the battery has a input voltage of 5 volts. And the input of the logic gate would be at logic 1, while the output is at logic 0 and at 0 volts. Right? It was discussed in a previous episode that a light-dependent resistor has a resistance that is inversely proportional to the intensity of light. So in this case, during bright daylight, its resistance drops to about 100 ohms, right? But in the dark, the resistance of the LDR is about 1 mega ohm, and this causes the potential at point A to drop to below 0.4 volts. Okay? The input of the NOT gate is now at logic 0, and the output is at logic 1 or nearly equal to 5 volts. We say that the current from the output flows through the LED and light it up. So it's called automatic light switch because the switching is not done manually, as in the case of ordinary kind of switches. Right? What triggers this, what we call LED to light up, is the use of a photocell or an LDR. All right? Depending on the amount of light that strikes the photocell, okay? Of course, with the use of an inverter, the type of gate used here is a NOT gate. Okay? The NOT gate, remember, it inverts the input. When the input is logic 1, the output is at logic 0, or vice versa. If the input is at logic 0, the output will be at logic 1. Right? Our second example is about a time delay switch. Okay, this circuit diagram shows a time delay switch. This is the kind of switch used in some cars, right? It is the door that operates the light switch. When the door closes, the light stays on for a few seconds before going out, all right? And as can be seen in the diagram, this circuit uses an AND gate. That's a symbol for an AND gate, all right? Notice that there are two input terminals connected just to uh, one terminal divided into two, all right? These two inputs are connected together. So when the input or inputs are at logic 1, we'll have an output that is at logic 1, all right? Uh, when the switch is closed, meaning the door is not yet closed, all right? When the door is not yet closed, the switch is still closed, all right? Making point A in the diagram at 5 volts, okay? So both inputs of the AND gate will be at logic 1. So the output is at logic 1 and the LED is a light, all right? So take note, before closing the door, uh, the uh, the switch, all right, the switch is still closed, okay? And the driver can notice that because the LED will produce light. So that's an indicator, right, to remind the driver that he has not yet closed the door or locked the door, right? And what happens if he he now closes the door? So when he closes or locks the door, then the switch now is open. So when the switch is open, all right, uh, that means there will be no more current from the battery, all right, that would produce the necessary voltage, all right, at point A to allow the AND gate to operate, all right. So when the switch is open, it is now the capacitor that provides the necessary current, okay. When the switch is open, just like now in the diagram, the charge on the capacitor slowly flows through the resistor until point A is at 0 volts. So while the capacitor is discharging, that means allowing the input, okay, to the AND gate to be at logic 1. All right? In other words, making the LED a light, okay, for as long as the capacitor is discharging, okay, sufficient charge or current, the LED will remain a light. But for how long? All right? The length of time for the capacitor to provide the current is what we call the time constant. All right? Time constant, or in this example, is what we mean by the length of time that is delayed. All right? It's just equal, numerically equal to the product of the resistance R multiplied by the capacitance. That's why you notice there is a resistor of 100 kilo ohms, okay, connected across the capacitor, right? So when you multiply 470 microfarad to 100 kilo ohm, but there is a need to convert the units to the SI into the SI system, meaning 100 kilo ohm has to be in ohm. That means 100 times 10 to the third power ohms, while the capacitance has to be in farad, and that means 470 times 10 to the negative 6 farad. All right. So calculating for the time constant, we will get 47 seconds. 47 seconds is the time during which the LED is alight. All right. It goes off only if the capacitor stops discharging, making the voltage at point A equal to 0. So when that happens, the input to the AND gate will no longer be at logic 1. All right. So logic 0 will be the inputs, and therefore the output will be at logic 0, switching off the LED. That's why it's called a time delay switch, right? Because even if the switch here is already open, meaning there will be no more current generated from the battery, it is the capacitor that provides momentarily providing the necessary current, all right, for the AND gate to operate at logic 1, right? So that time is just enough. 47 seconds is just enough, all right, for the driver to settle down upon getting into his car, and when the LED stops or is switched off, that means he's now ready to drive. All right. So we call it a time delay switch using only this setup, specifically using an AND gate together with a capacitor and of course as an indicator the LED. For our questions 1 and 3 or 1 to 3, we have the following figure that shows a circuit used in a car door and seatbelt warning system. Alright, so this is the symbol for the door switch. Alright, and this other symbol represents the seatbelt. Alright, the switch for the seatbelt. And there are two gates shown here. This is the OR gate. The two input terminals labeled D as in door, right? The first input terminal to the OR gate is the switch representing the door, all right? And the other one is uh, the seat belt. So S stands for seat belt and D for door. Now, there's a second and a logic gate, AND gate, and that input represents the ignition, right? The ignition, because over here you have the ignition switch. So when this switch is closed, that means there is current that is able to flow into the AND gate, and that is represented by the terminal I. The output of the AND gate is labeled B. All right. So over here, of course, you have the buzzer. It is the buzzer that will uh, sound or that will buzz to indicate, all right, to indicate or to give the signal. Either the driver has not yet worn the seatbelt or he has not yet locked the door. Okay, that is the purpose of having a buzzer or a warning door and seatbelt warning system, right? So, what are the questions for this particular what do you call logic gate applications? So here are the questions. Number 1, what two logic gates are used in the circuit? Question number 2, complete the following truth table for the circuit. All right, we already have laid down all the conditions for the three switches, the ignition switch, the door switch, and the seatbelt switches. All right, so all the necessary or possible combinations are already given. All right, all you need to do is provide the necessary logic state, either logic 1 or logic 0, all right, in the fourth column representing the buzzer. So the third question is for you to explain briefly how the alarm works, okay? Meaning what voltage is established at each input when the switch is on or off. And specifically, under what conditions will the buzzer sound, right? So you can what do you call this? You can describe the conditions for the buzzer to sound if you're going to first fill this up. The truth table is completed first, all right? And remembering that if the ignition input is at logic 0, that means the ignition switch is off, all right? If the logic state for the door switch is at logic 0, it means that the door is locked. And if the switch for the seatbelt is at logic 0, it simply means that the seatbelt is already fastened. Alright, so we shall see the answers in a little while. Alright, so for our solution, we begin by completing the truth table. Alright, we have here the given logic states for the ignition switch, the door switch, and the seatbelt switch. So all we need to do is determine what the output of the AND gate would be. That's at point B. Alright? Alright, so if I is 0, input I is 0, alright, input D is 0, and input S is 0, okay, the output at point B would be, of course, 0. Okay? So we continue. If I is 0, D is 0, and S is 1, alright, uh, what will be the output at point P? Again, it is 0. Okay? Again, to continue, if I is 0, D is 0, I mean 1, and S is 0, alright, what is the output at B? Alright, so 0, 0, that still be 0, right? So we continue filling this up until we have completed them, alright? So for 0, 1, 1, our output will be 0. For IDS 1, 0, 0 respectively, okay, the output at B will be 0. For IDS 1, 0, 1 respectively, our output at B would be 1. Alright? Because the two inputs I here and the output for the OR gate is also 1. That makes point B at logic 1. And likewise, for IDS to be 1, 1, 0 respectively, we also have logic 1. And finally, for IDS to be at logic 1, 1, 1 respectively, the output at point B also will be at logic 1. So we've just completed our truth table. Looks like that there are only 3 conditions, all right, for the output at point B to be at logic 1. Okay, in other words, these 3 conditions, okay, will tell us when the buzzer is going to produce sound. All right, so continuing with our answers, we now summarize the results of our truth table. So we have here the 3 conditions where the output at point B would be at logic 1. All right, so we now specifically answer the 3 questions. For question number 1, what 2 logic gates are used in the circuit? Of course, we have the AND as well as the OR gates. Question number 2, as shown in the truth table, we already have completed, all right, the logic states. And for question number 3, these are the conditions for the buzzer to sound. Number 1, or letter A, the ignition switch is on, right? And the door is locked, but the seatbelt is not fastened. So that's indicated by the first condition here, all right? Ignition, when you say ignition is switch on, that means the I is at logic 1. Okay. The door is locked, therefore the door switch has or is at logic 0. And if the seatbelt is not yet fastened, that means uh, the, the logic gate for the S switch is at logic 1. All right. Now the second condition is when the ignition switch is on. So that means I switch is at logic 1 and the seat belt is fastened. So when the seat belt is fastened, that means the logic state is at 0, but the door is unlocked. So if the door is still open or unlocked, okay, the switch for the door is still at logic 1. And the third, of course, is when the ignition is on, all right? That means ignition I is at logic 1. The door is not locked. So when the door is not yet locked, the door switch is at logic 1 and the seat belt is not yet fastened. So the seat belt switch is still at logic 1. So these are the 3 specific conditions for the buzzer to produce the sound. In other words, when all of these 3 conditions or any of these 3 conditions, okay, is met, all right, the buzzer will produce sound to remind the driver, okay, to remind the driver, for instance, if he has not yet locked the door, even if he's already fastened his seatbelt, all right, if he has already fastened his seatbelt, the buzzer will sound because the door is not yet locked. But even if the door is already locked, but he has not yet fastened his seatbelt, then the buzzer will sound. Or if both the what do you call the door still unlocked and he has not yet fastened his seatbelt, the buzzer will of course sound. But all this only happen if, okay, the ignition switch is at logic 1. In other words, you have to get the car started. I mean, the engine has to be started, right? For all of these conditions, okay, to happen, it is important that the ignition of the car engine has already been started, right? For our last question, we will be referring to this circuit diagram of an automatic greenhouse waterer. All right, so as shown, uh, there are two gates. Okay, we have here the AND gate and again the OR gate. All right, and you see again here an LDR, okay, or a photocell, ORP12. Okay, we have what we call contacts. When you say contacts, this represents the switch, okay, that is installed, okay, on the soil, all right, on the soil to what you call to describe whether the soil is dry or wet. So that is what is meant by the contacts. And there is an override switch over here, all right, an override switch. Of course, the usual variable resistors. There are two, a 10 kilo ohm variable resistor, okay, that is connected to the photocell or the LDR, as well as another variable resistor connected to the contacts. That's for safety purposes. No? Variable resistors can be adjusted, all right, as the name of the resistor implies, all right. You can set the right amount of resistor, okay, that will enable the light-dependent resistor to operate normally, right? Or in other words, without being damaged due to uh, possible increase in voltage or in current. And so with the switch for the contacts, there is a resistor that acts, okay, for as a safety precaution. So the inputs to the AND gate, of course, labeled A, all right, input A is connected to this LDR, while the other input for the AND gate is the one connected to the contacts. While for the OR gate, we have two inputs, the output of the AND gate, which is labeled C, and the input of the OR gate is the one that's connected to this override switch. And the output of the OR gate, okay, is connected to what we call an inductor or a coil. This coil, the principle is or has something to do with electromagnetic induction, right? It is the one that will what we call affect the switch of the water pump, which operates in an alternating current, all right? So depending upon the result of the output of the OR gate labeled point E, okay, if the amount of current or if point E is at logic 1, that means there is enough current that will establish a magnetic field in our coil sufficient enough to possibly switch on the water pump, all right? But if output E is at logic 0, then that means there will be no current that will switch on or off, or that will switch on the water pump. So that's basically what this circuit diagram of an automatic greenhouse water is all about. Right? We'll see the specific questions in a little while. Alright, so an automatic greenhouse water, um, the circuit is designed so that water pump switches on when it is dark and the soil is dry or an override switch is used. Okay, you may refer back to the circuit diagram. Here are the specific questions 4 to 5. First, you have to construct a truth table for the two logic gates, right? So, as soon as you have the truth table for the two logic gates, you can uh, work on your task by completing the given paragraph, okay, which we shall see in a little while. Okay, you have to complete the given paragraph by supplying the correct words, right? And then from that, describe the logic states necessary to switch the water pump on. Okay, relate these logic states to the functions of the LDR, the contacts, whether wet or dry soil, and the switch. Here is the paragraph that you're going to complete. When it gets dark, the resistance of the LDR blank to 1 mega ohm. Point A rises to a potential above blank and is at logic blank. When the contacts are wet, they have a blank resistance and point B is below blank. When the soil dries out, the resistance across the contacts blank. The potential of point B is blank and is at logic blank. As both inputs of the AND gate are at logic 1, the output is at logic blank. The output of the AND gate is one input of the blank gate. When this input of the OR gate is at logic blank, the output is at logic 1 and the pump is switch blank. If the switch is blank, point D is at 5 volts, logic blank. This means that the output of the OR gate is at logic blank, no matter what the other input is. The switch is an override switch. We now have the answers. When it gets dark, the resistance of the LDR rises to 1 mega ohm. Point A rises to a potential of above 3.5 volts and is at logic 1. When the contacts are wet, they have a low resistance and point B is below 0.4 volts. When the soil dries out, the resistance across the contacts rises. The potential of point B is above 3.5 volts and is at logic 1. As both inputs of the AND gate are at logic 1, the output is at logic 1. The output of the AND gate is one input of the OR gate. When this input of the OR gate is at logic 1, the output is at logic 1 and the pump is switched on. If the switch is closed, point D is at 5 volts, meaning at logic 1. This means that the output of the OR gate is at logic 1, no matter what the other input is. The switch is an override switch. Alright, so for our detailed answers, we have the truth table, and based on this truth table, we can say that output E is at logic 1 if, number 1, the override switch is closed. meaning at logic 1, no matter what the state of the other input to the OR gate is. And number 2, both the inputs A and B at logic 1, even if input D is at logic 0. Alright, that's the meaning of uh, getting this results of our truth table. Alright, when is the output at point E, B at logic 1? Alright, so you will notice here, this combination, that one, that one, and this one. And we summarize, okay, the conditions for output E to be at logic 1 into just 2. Okay, and these are the two conditions, which when translated, we say that the water pump is switched on if, number 1, the override switch is on regardless of whether it is dark or not, or whether the contacts are dry or wet. And the second conclusion is the power pump is switched on if it is dark and the contacts are dry, even if the override switch is off. That ends our video tutorial for this particular part of the series. Thank you very much for your indulgence, and please don't forget to subscribe.